Okay, well, good evening, everybody. Thank you for having me representing Shetland Geological Society tonight. And I'm hopefully going to enthuse you a little bit about rocks. And the great thing about the sort of, well, this is wintering wild and well, and rocks are especially good for winter because unlike wildlife, they don't move. Or let's say they do move, but they move so very slowly that there's no chance of you missing them if you want to go out at any time of year, day or night. They're going to be just where you wanted them to be. Now, I've started with a welcome to Shetland slide because unless you have a knowledge of Shetland's geology already, which probably some of you do, then I feel like I am kind of welcoming you to a new place entirely. And I say this because I first came to Shetland, well, as a fetus, actually, but I spent all my childhood summers here. So I was very familiar with the Shetland landscape, but knew not a thing about geology until I started with the Geopark as a coordinator. Why did I get that job? Because it was about doing promotion and interpretation and education, which I had done. It was just I needed to learn the geology bit. And thankfully, Alan Fraser, who some of you probably know, was incredibly generous with his knowledge and time and educated me. And it completely transformed Shetland for me, transformed the way that I see it. And I just find it terribly exciting. And I just want to say, lest I forget, that the book that we just mentioned, I helped with it, but Alan was the main force behind that book. He was the main author. But I'll tell you a little bit more about that towards the end. So, I mean, you can see that Shetland was full of lots of different colours on that map, and that represents lots of different geological units, we'll call them. And I said that rocks move very slowly. You're probably all familiar with the idea of plate tectonics, the idea that continents are drifting very, very slowly around the world, and oceans are rifting. The Atlantic is getting bigger as I speak, and the Pacific Ocean is shrinking and eventually will close and we'll end up with a big supercontinent. So this is something that happens repeatedly. And in terms of Shetland, over the last 700 million years, this slide is giving a bit of an illustration of the route that we have taken from near the South Pole up to where we are now, nearly at 60 degrees north. But the key thing is that over that time, Shetland, it's not just been one single thing. It's actually the result of several different blocks, different geological units that have formed in different times and places, being brought together as continents have shifted around, brought together along fault lines, essentially. Now, if we look at this map of Scotland, which is renowned for its geology, you can see that there's a range of colours there. And I mean, Scotland really is the birthplace of modern geology. James Hutton, who was really the father of modern geology, it was from his observations in Scotland that the science was born, when he realised that the Earth was just much, much older than anyone had ever anticipated. We were talking millions rather than thousands of years. And, you know, he figured out that the present was the key to the past. And by looking at the rocks of today, we could figure out what had happened, you know, hundreds of millions of years ago. If you look at the map of Scotland, then you look at Shetland, you'll see we've got most of the same colours. The only bit we're actually missing is the dark blue bit to the very northwest of the Scottish mainland. We don't have that. But the rest of it, we have all of these different units, but just in a much smaller area than Scotland. So it's kind of incredible, really. I don't know that there's anywhere else in the world of this size that has that much diversity. And for someone like me that came into geology, the Geopark, knowing like literally nothing about geology at all, once you've kind of got to grips with Shetland, it is almost like you've covered a geological degree, because it just, all the major geological concepts and processes are evidenced in our islands. So I'm going to give you a very whistle-stop tour of the different units that we have, but I'm not going to get too bogged down in the actual geological processes, because I really just want to show you the pictures of the cool places. But our earliest rocks are about 2.3 billion years old. When they formed, the atmosphere was methane, the sky was pink, the world would have looked very different. The kind of only life forms really were stromatolites. And the earliest rocks, or the oldest rocks that we have, which you can find in places like Oya, they actually started life as lavas, essentially. We can see the volcanoes here erupting out lava. But over the years, those rocks have been squished and squashed in different continental collisions until they've become what we call metamorphosed or changed. And they are, we can see on the map here, there's little pink areas where we can see these really old rocks. So that's one of the units that we have in Shetland. I'm just showing you this picture because a Wilson cycle is basically the cycle of an ocean starting. So you have something rifting, a little bit like the African Rift Valley today. An ocean spreads like the Atlantic Ocean is currently spreading. Eventually it stops spreading and starts to contract again, as the Pacific is doing now. And eventually you get a continental collision and a mountain chain will be pushed up somewhat like the Himalayas today, which is still growing. And Wilson cycles happen over about a 500 million year period. So between our earliest rocks, 2.3 billion years ago, and today, there's been time for 4 or 5 Wilson cycles. So our oldest rocks have really been quite squished and squashed. And even our second oldest rocks, which we call the Moyne, they were actually metamorphosed when this ancient continent Rodinia formed. They started life as actually sediments that had eroded into an ocean. And when that ocean closed and a big continent was formed, those sediments were all squished and squashed to make our Moyne rocks, which we find primarily in Yell. And although the story of their birth isn't particularly exciting, it doesn't involve like volcanoes or explosions or anything, but I have to say Yell does have some of the most beautiful rocks in Shetland, without a doubt. And I just want to make a little tribute here to Mike McDonnell, who some of you might have known, who passed away a couple of years ago, but just recently had an exhibition in the museum in Shetland, and he did a great project with the school children in Yell that was basically celebrating the beauty of the Yell rocks. And Mary Ellen Odey, who some of you may also know, the sister of Bobby Tulloch, the famous naturalist, and also a cousin of mine, she had the idea to call it Yell, it's Moyne and it's nice, which is a little geological joke. We then come, so our Moyne rocks are about a billion years old, so much younger than our oldest rocks, but still pretty old. Then we get to what we call the Dalradian, which formed in a similar way to the Moyne. It started off as the sediments that had eroded into an ocean that subsequently closed, and the sediments got metamorphosed, got changed, got made into rocks as a big mountain chain was pushed up. And ultimately, a supercontinent called Pangaea was formed. So our Dalradian rocks are about 500 million years old. So we're getting younger, but we're still pretty ancient. And they form the spine of Shetland, so all that green on the map there. And they are actually, what you're looking at when you're driving along the Lang Cairns, you're actually looking at the roots of an ancient mountain chain, which we call the Caledonian Mountains. Now that mountain chain formed when an ocean called Iapetus closed about 420 million years ago. And in fact, although we just see the very remaining roots of those mountains in Shetland as just like low hills, the Appalachian Mountains in America are part of that same chain, but they formed slightly later as a continent was closing. You know, the Shetlandy bit got formed first, and then the Appalachians slightly later, but it is all part of the same mountain chain. So when Pangaea formed, when the Iapetus Ocean closed, Shetland was kind of sitting where you can see the UK, the little red splodgy bit on the map there. And we were kind of sitting in the foothills of a mountain chain, somewhere near the equator, in a desert environment. And mountains were eroding at high speed and basically laying down lots and lots of sediments, huge quantities of sediments, which we now call old red sandstone. And you see them in the southeast and the west part of Shetland. And the old red sandstone, so you see that in the southeast and the west part of Shetland. And the old red sandstone is about 400 million years old. So still very old, but actually pretty much some of our youngest rock now, we'd have to say. So Shetland is rightly termed the old rock because it is old. And I don't know if it's if that's just me being a bit hippy trippy, but I do remember going to Iceland some years ago, and obviously that's new because that's forming as we speak at the mid-ocean ridge of the Atlantic. And you've got volcanoes creating new land all the time, and I just felt that was so like alive and energizing being there. I don't know if it was to do with the rocks, whereas Shetland's rocks, because they're so old, it's just much calmer. That's just me being a bit weird. But if you look on the little map in yellow, I'm sorry it's quite small, but you'll see that there's various lines. These are fault lines. And it's the reason why Shetland is so diverse is because of these faults, basically. Because these different blocks of rock that have formed in different parts of the globe at different times through different mechanisms have come together along fault lines. And you'll see that Orkney there has completely not got a single fault line running through it. So Orkney is primarily actually old red sandstone. So it's quite interesting that we've got these two island groups next to each other, and yet they're so geologically different. The final kind of major group of rocks I'll mention in Shetland is what we call the Caledonian intrusions. And this is basically big upwellings of magma that have come from the mantle. But rather than erupting out as a volcano, which also happened, they've cooled quite slowly underneath the surface of the earth. And that can happen either when a mountain chain starts to subside and rift. Decompression can cause that magma to come up, or sometimes it can happen because a melting ocean floor as an ocean closes actually causes magma to come up. So there's different ways that it can happen. But ultimately, the key point is that this magma has solidified into granite, which forms our highest point today, Runner's Hill. So it's interesting to think that, like Runner's Hill, 450 meters high today, actually started life away underground in the roots of a mountain chain. And all of the mountain that was on top of it has eroded away, and it has been uplifted and now stands proudly as our highest point. And you can see with all the red there on the map where you'll find different intrusions. I'm not going to labour the point about oil and gas because we can't really visit it on our landscape, but we are aware, of course, that Shetland's present day wealth very much comes from the fact that North Sea oil was discovered in the 1970s, and there's a whole fascinating story behind that. And actually, I love this map just because, like, I didn't realise there were so many oil fields, and it's kind of fascinating to me. But I won't go into that now. I don't want to get off at a tangent. The other thing that we've had that's once all our rocks have come together along these faults, creating this almost this jigsaw, then the land has actually been carved and shaped by multiple glaciations, by glacial ice, as it has flowed across. It's carved out the land and created different landforms. And interesting thing about Shetland, during the last glaciation, so about 12,000 years ago, Shetland kind of had its own ice cap, separate to that of Scotland and Scandinavia. And the weight of ice on Scotland and Scandinavia was several kilometres thick, was absolutely huge, and forced those land masses down. And Shetland only had a relatively small ice cap of its own. So Shetland was actually sort of pushed up as the crust sort of bent. And what's happened since the ice melted is not only have the sea levels risen with the ice, but also Shetland has been sinking as Scotland and Scandinavia have rebounded. So Shetland is essentially a drowned landscape. We also, this is just a little cool picture that I got from Oyer, from Fuglaness, where there's actually evidence of interglacial peat formation. So this is, we've got a layer of glacial till that was deposited during the last ice age 12,000 years ago. And then we actually have a layer of peat, and there's actually like trees, like actual branches coming out of it that are about 125,000 years old. So that's just incredible. But as I was saying, Shetland is basically a drowned landscape. Sea levels have risen and Shetland has sunk at the same time. And so when you're looking here, I'm down from Wormadale, and you see all the little islands. I mean, they're basically the tops of hills. If we were to drain all that water away, you just see a lot of hills. but water has filled up the valleys to create the vaux that we know and love. We also just occasionally have had episodes where there have been tsunamis, and we can find evidence of this in our landscape. And you see in that picture there, there's just like it's a layer of peat with a big layer of sand running through it. And that was from about 8,000 years ago, an episode called the Storegga Slide tsunami, when basically a big load of like landmass off the coast of Norway kind of subsided and caused a huge tidal wave, which basically engulfed Shetland. So you can see from that that sort of whistle-stop tour, which basically told you like an entire geological degree in 20 minutes, that we just have this incredible variety. And you can see from this simplified map with those major faults going up through it, this sort of incredible jigsaw with, say, rocks dating from about 2.9 billion years old to about 400 million. So quite impressive. So what I'm going to just do now is run you through some of the highlights that you can see if you get out, and just to try and give them a little bit of context in terms of their modern day equivalent. So we're all familiar with volcanoes, and you'll be aware of Mount St. Helens that had a massive eruption in the 1980s and the huge pyroclastic flow. We have one here. So this is a diagram of a stratocone volcano, which was drawn by my great friend Elizabeth Pickett, who's a geologist and all-round good egg. And this is an explosive volcano. You know, you're not just getting a little dribble of lava here and there. You really are getting big, powerful eruptions that are ripping stone out of the volcanic vent, and you're creating these huge clouds of ash and dust and gas that cascade down the sides of the volcano at 100 kilometers per hour, just wiping out everything. And that's what we have at Eshenes. So these cliffs here, this is the remains of a 400 million year old volcano, essentially. And you can actually see on the left where that little hammer is, all those little different bits and bobs. It's like the rock's made up of all different bits. That's basically been an explosive eruption, and all of these blocks have then cascaded down and been cemented into this rock, which we call agglomerate. And if you walk to the Eshenes lighthouse, you can walk on that. And I know from people that have been to more recent volcanic landscapes that they can't believe that it's 400 million years old, because it actually looks so fresh. But as we walk along the Eshenes coast, you can start to see sort of the red layer in the photo on the right there, that kind of ashy red layer, and lava flows beneath. And it's kind of interesting as well here, because you can see that the cliff kind of comes down, and then there's like almost a platform, a step, and then it goes down into the water. Now that step can't have been cut recently, because the sea level hasn't been that high since the last glaciation. So we know that that kind of little steppy bit, that's been cut like in a previous time before the last glaciation, when the sea level was higher. In the far distance of that photograph, you can see Muckle Ossa, the little island, and we think that that's probably the remainder of the main volcanic vent, because it seems to be surviving where the rock around it has eroded, and that's probably because it's a slightly tougher rock. But essentially, as you walk north along from the lighthouse up to the Grindlanavir, you're walking through the flank of a volcano. It's the best one you can walk through in the UK, and you're kind of walking through older and older lava flows, and you can see them here just in the landscape. And the other cool thing about the coastline here, of course, is that now it is one of the highest energy coastlines in the world, because it's got the Atlantic just coming across from America with nothing impeding it, essentially. So of course it's doing great damage to the coastline, and it's carving out things like the big gyo called as gyo at the lighthouse. Under the land just to the north of that gyo is actually the biggest sea cave in Britain. And in fact, the Hulsa Skrada, which we've got on the left here, that would have started life also as a sea cave, but ultimately the roof's fallen in, and eventually the whole thing will fall in, and you'll just have another gyo. And then on the right, we've got the Grindlanavir, where the powerful seas have actually come in through gap in the rock and basically thrown up huge blocks, some of them the size of small cars, thrown them 50 meters inland. So it does demonstrate the power of the sea. And I just think it's amazing, this site, the Grinds of the Navid, because you've got all that modern day power and force, but also the rock that you're looking at there is ignimbrite, which is basically formed from a pyroclastic flow. So another really high energy, event. And if you go there and you look at the rock, the ignimbrite, you'll see little orange streaks in it, which are little squashed lava droplets. So we've talked about volcanoes. Moving on, just sort of looking at the Sierra Nevada, which in modern day America, we've got the Pacific Ocean closing, and we've got an ocean plate, basically a bit of ocean floor descending beneath it and melting, and that's causing magma to well up. And that's what we've got essentially with Runners Hill. We've got a big upwelling of magma. And again, it is kind of, because this was formed underground very slowly in a very hot, clearly, environment. It's molten magma that's cooled very slowly. But yet today, it's our highest point. It's actually got a climate as extreme as any Scottish mountain. And it is home to like plants that you would normally only find in the Arctic Circle. So it's gone from like a birth of being like hot magma to just being this like barren, cold, windswept, almost Arctic landscape. So I just love the contrast. Like, then you can see just the power of the different kinds of forces and activities in nature. San Andreas Fault, big fault line in Canada, all probably aware of that. We have our own. So looking again at this little map with the faults on, we have what's called the Walls Boundary Fault, which is an extension of the Great Glen Fault, which runs up through Scotland, creating, Loch Ness and the lochs along that line there. And the Great Glen Fault is one of Europe's major tectonic features. And in Shetland, we have actually the best place where you can see it exposed, and that is here at Backsand at Ollabry. You can see this huge sheer wall there of granite, which is on one side of the fault, and then on the other side there's much softer metamorphic rock which has eroded away, exposing this wall of rock, basically. It's an incredible beach to look at. You have to be careful. You can scramble down. Don't go on your own. You'd always be with someone, because it is a bit of a dodgy scramble, but well worth it if you are competent to get down. And you get onto the beach and you see all this evidence of massive, like, folded rocks that have been basically smushed as that fault line has moved. And it was last moving about 170 million years ago. And it's actually moved in one direction and then it moved back in the other direction. So there's just been all kinds of hellery going on there. And on that beach, you'll see some amazing, amazing things. You've got the big folding like this. You can see the woman there and the size of that. And then you get like tiny little folds in rocks as well, these pygmatic folding. Absolutely stunning. Look, tiny, look, that's my Carmex. So you can see that's a little tub of Carmex, which is what, about 1.5 inches across. See the tiny little folds. So on this beach, you've got like massive, like archy folds, and then these tiny little things all formed by that fault movement. And then we've talked about the volcano, and we've talked about the magma melting, and we've talked about the fault. And if you go to Braywick Beach, you get all three in a oneer. It's like 3 for the price of 1, because that beach just below the Braywick Cafe, that has a fault like running straight down the middle of it, the Melby Fault. And on the eastern side of that fault is granite. So a rock that was formed, deep in the roots of the mountain chain that cooled really, really slowly. But because there's been a fault on the other side, it's ended up sitting next to a whole load of volcanic rocks, which I'll show you in a moment. But I'll just point out as well, on this photo with all the people on it, sitting on top of the granite is a massive, like 2 or 3 meters worth of glacial till. And all of the sort of granity, pinky boulders on that beach, they've fallen out of that till. They've probably been dragged there from near Mavis Grind or the Niben area up to that beach. But you say you've got that at one end, and then at the other end you can see here you've got basalt, you've got evidence of a mud flow, you've got some old red sandstone that presumably this volcano was erupting onto. You've got a whole mess of, I don't know what's going on in this picture, but there's been stuff that's been erupted and splattered down. Here, this is like fascinating, just like so completely random, because it's in this section of beach that's maybe like 50, 60, 70 meters long. You've got all of these different rocks going on. And this one, the stripy one, this is actually evidence of a sort of sandstone that was laid down in a lake environment. But the interesting thing about it, you can see the stripiness. And actually, if you were to drop a bit of hydrochloric acid on the red stripes, the browny red stripes, nothing would happen. But if you drop it on the grey stripes, they fizz because they've got calcium in. So that's giving us like evidence of maybe fluctuating water levels and concentrations of calcium in the lake over time. But say if you walk 50 meters, you've got basalt lava, you've got andesite lava, you've got mud flow, you've got sandstone laid down in a desert, you've got sandstone laid down in a lake. And all of this was happening like 400 million years ago when Shetland was sitting near the equator. It is quite awe-inspiring. And then we go to the South Mainland, and I mentioned, you know, at around about this time when Shetland was near the equator, we were sort of in the foothills of some mountains that were essentially eroding very, very quickly into a desert environment. Now, occasionally you would get flash flooding, which would cause sort of temporary lakes to build up and to form. And when I say temporary, I'm like talking they'd be like for 10,000 years or more, not like a week. But it was a very, again, active landscape, and we have evidence of that here in the south end of Shetland. So if you go to the beach, to the Ness of Bergy, you see all of these cobbly things. This is basically the remains of an alluvial fan deposit. So when mountains erode, you have like cobbles coming down them in rivers, and they'll sort of go fairly quickly down. And then when the gradient lessens as they reach the bottom, they'll sort of all the big heavy stuff will just be deposited, and you get these alluvial fans that grow out into the desert. So we've got evidence of that at the Ness of Bergy. In fact, we've got evidence of maybe an alluvial fan that has then been even redistributed further as another flash flood has come along. At Quarf, it's pretty cool. We've actually got this kind of, where the stick is at the top, there's all this mishy-mashy mangledy material, and underneath it there's, you can see some quite straight formed sort of solid rock. That's the remains of an ancient scree slope. So we've got evidence of this sort of alluvial fan that's formed at the bottom of an ancient mountain, but now we've got evidence of a scree slope that's formed on the slopes of an ancient mountain. And this junction here between the sort of solid rock and the mishmash, that's called a nonconformity, and that represents a time gap. So actually between the solid rock being sort of metamorphosed and formed, there might have been 10, 20, 30 million years before this other stuff was deposited on top of it. So you know, you can put your hand on it and you're bridging you know, tens of millions of years with your fingers, which I always think is pretty immense. And here we go again, more of the conglomerate, as we call it, at Scatness. So evidence of this alluvial fan, but again, it's been probably then redeposited even further out into the desert plain by flooding. And so what you've ended up with is sort of layers of cobbles, and then maybe a layer of sand, and then you'll maybe get more cobbles. So it's just evidence of really, really dynamic landscape. And then we go to Aix-les-Bains along the southeast coast. And what we're looking at in these pictures is evidence of what's actually been going on a little bit further out in that desert plain, where we've basically had sand dunes forming. And what we're seeing in these cliffs here, these funny, you've got them sort of angled and then straight, and then angled and then straight. This is these angled bits are basically the front face of sand dune as it's been like progressing and progressing and progressing as sand dunes do. And if anyone studies these, they can work out, you know, what direction the wind was blowing when they formed. So yeah, it's just immense. We can know just what the environment was doing 400 million years ago. And then just a little bit south of there, we've got this place, Shingley, where there's been one of those temporary lakes that I mentioned. And in that lake, fish have managed to evolve and thrive. Presumably it's been connected to the sea at some point, and that's how the fish have managed to emerge there in the first place. But you know, you can go down there and you can search for fossil fish. This one on the right here, this is his like scientific name is Stegotrichellus finlayi, but I call him Bob because I was at the site with a couple of kids from Yorkshire, and there was two fish. There was Bob, and there was another one that was a little bit less clear, and they called him Blob. So Bob and Blob. Bob is still there, but he is sort of starting to deteriorate just with the weather. But obviously with the dynamic landscape, you know, more rocks are being, more bits are being uncovered every year. So you're always going and finding different fossils. Just be aware that you shouldn't take them away. That is illegal and also not fair on other people. Coming towards the end, I've got about 5 minutes left, but this is really one of our highlights. So this is a picture of the mid-ocean ridge in Iceland. So that area where the we've actually got seafloor spreading happening and new rock being formed. When you've got a seafloor, an ocean floor forming, like we have under the Atlantic today, you've basically got a big magma chamber basically under the surface, and that magma is sort of cooling and spreading and cooling and spreading and cooling and spreading, and some of it is also erupting out into the ocean to create these pillow lavas. But within the sort of the depth of the ocean floor, as it cools and spreads, you get all these different types of rock because different minerals form at different pressures and different temperatures. So you get all these different layers in the ocean floor itself. And what happened when Iapetus Ocean closed? Normally, your ocean floor that was part of the ocean would just sink down and subduct, as it says in this image at the top here. Plate will just melt back into the mantle. But occasionally, a little bit will get caught and pushed up, and that's what's happened in Unst-and-Fetler. So instead of that ocean floor sinking as it should have done, it's actually come up the way and rotated in 90 degrees. So when you walk across the eastern part of Unst, you're actually walking across the layers that were in that ocean floor 420 million years ago. And you also get to walk across the boundary, the moho, which is the boundary between the Earth's mantle and the Earth's crust, which would normally be about 30-40 kilometers below the Earth. And if you go to Norwich Beach, you can actually put a foot on continental rocks, so which were part of the ancient North American continent. And if you can do the splits, which I can, you can have a foot on continental rocks and a foot on the ancient ocean crust that was pushed up on top of them. And that line, that orange line there, kind of represents the thrust. And here, if we go up to the Hyogs, we can actually step across the moho into the Earth's mantle, which is forming the Hyogs, the high ground there. And Hagdale, within that ocean crust, we also get minerals forming, and chromite was, you know, a big industry in Unst at one time. It was the largest chromite quarry in the UK. So as well as just telling an amazing story, our rocks do have also practical applications. And this middle picture here is showing bands of this dark bands, which are chromite. And the people used to follow the bands, trace the bands until they'd find a big deposit of chromite that they could then mine. And this is just Whatley and Sobel examples of the different types of rock that you walk through in Unst when you're walking across those different layers of ocean floor. So we've got what we call whorlite, pyroxenite, and ultimately gabbro at the top. And then at Hamness in Unst, you actually are standing on basically what was at the very, very top of the magma chamber. You get these little offshoots called dikes, little offshoots of magma, and there's I think that's Paul Harvey's Welly next to a magma dike there. Then you go to Fetler, and you find this weird squished rock called the Finny conglomerate. So this was basically, if you imagine those cobbles that we were looking at Scatness, the Nessabergi, that sort of alluvial fan type cobbles, you've had a layer of ocean crust that's been pushed up, you've had mountains eroding into cobbles, and then you got another layer of ocean crust pushed up, and it squished the cobbles and then eroded away, and it exposed all of these stones, which used to be just round cobbles, and they're now like squished long tubes of rock. And it's like, just to imagine the force that actually did that, and now it's exposed for us to just go and wander over at Finny Beach. So I'm just going to finish up my last few slides with just some examples of, as I mentioned, the rocky resources, because we have exploited the geology of Shetland. And I mean, it's okay to exploit it, but I think it's better to do that as little as possible and actually just enjoy it for what it is. But I mean, looking at the 20th century here, I mean, I think there's a whole like study to be done in terms of like Shetland building styles, because wherever you are in Shetland, you've got to use the rock that you've got. Now, if you're in Bresser, you've got lovely sandstone that splits and makes great building blocks. If you're in Fetler, like, I don't really know what to say about that. It's crazy. And then Mucklerow, you've got granite, which is, you know, quite nice to build with, but pretty tough to chisel, I would have thought. And if we go backwards in time from the 20th century to the sort of Norse period, and these are some of the longhouse excavations that took place in Unst a decade or so ago. And Unst has the highest density of Viking longhouses anywhere in the world, and that is because they're made of stone, whereas in Scandinavia, for the most part, they'd be built of wood. So they've survived in the Shetland landscape. Then we go back a little bit further to the brocks, the Iron Age brocks, and again, you know, thinking about the different materials that you can use to build them. Musa again is sandstone, so you know that's a great building material, and it stood the test of time. You've got Culswick here, which has used granite, which is a whole different kettle of fish. And then here at Hooland on the Eshenes coast, they actually made use of that ignimbrite, the pyroclastic flow rock that I showed you with the little streaky bits in, and that they would have had to use that rock. They actually brought it, you know, about 1 kilometre from where the source of where it was to build the broch, obviously recognising that it would do a good job for them. Going back even further than the Iron Age, go back to the Bronze Age, people were using rocks to heat water, and we have the like burnt mounds, remains of burnt mounds all across Shetland, and of course there's this example in Bresser where a burnt mound that was eroding into the sea was actually moved stone by stone and rebuilt. A burnt mound is really just a pile of burnt stones, and sometimes that's all it is, but sometimes it has structures associated with it, like this one did, including a hearth and a tank, and people were using these, they were heating rocks and using them to heat water for who knows what. But we tried doing lots of things with it, and we've managed to brew beer and dye fleece and clean cowhide, so lots of options. And then I don't really want to say too much about our Neolithic architecture because it's really quite minimal and a little bit dull compared to Orkney's Neolithic architecture, which I'm just throwing in there because my theory, which is held up by nothing, is that the reason geology Orkney has such amazing Neolithic architecture is because it has sandstone that splits into these big blocks that are just so great for building that like monumental architecture. And then, of course, we've got the felsite knives, which you can see in the museum, made of what we call spherulitic riebeckite felsite, if we can say it. And these were obviously, this rock was recognised back then as being something beautiful and worth just having for display purposes. I'm not going to say ceremonial or ritual, which is what archaeologists always say when they don't know, but I don't think they were using these knives for work. I think they were just like reveling in the beauty of them. And then you've got making your artifacts. Like the Vikings were using soapstone. It was like their Tupperware. They could make use of soapstone for lamps and for fishing weights and for loom weights and for bowls and for bake plates. And if you go to Catpund, you can actually see the remains here in the hillside of a quarry where the Norse have been quarrying out soapstone, and you can still see the chisel marks where they did it. Hagdale Horse Mill in Unst. This is a place where they were using this horse-drawn wheel to crush chromite, which was used for chrome plating and making the yellow pigment in paint. And then we've had copper mining in the south end at Sand Lodge, and this amazing thing at Garth's Nest, just this huge ore deposit, which we think was actually basically formed from a black smoker, which is like when you get underwater, kind of a big plume of hot fluid erupting up through the seabed and depositing minerals, and that's a black smoker, and we think that that's what formed this. But I mean, just looking at that and standing on it is incredible, really. Anyway, 45 minutes. Well, Helen was talking for the first 10, so I think I didn't do too badly there. But yeah, so I mean, thanks for listening to that. I appreciate there was a lot, but the thing to do is just to get out, explore it, experience it, enjoy it.